Anyway, today we have Dr. Matt Greenhouse. Matt is a recent retiree. He just retired in September, and we're looking for him to come regularly to our meetings. Anyway, Matt, he's retired from the lab for observational cosmology. He got his started out in infrared astronomy back in 1979 at the University of Arizona and Stewart Observatory. He got his PhD in physics from the University of Wyoming, and then did grad work on the Wyoming Infrared Observatory. In 1989, he came to Washington and to the Smithsonian, where he got a career started in astrophysics. 1996, he moved over to Goddard and joined the lab. So he's been on a number of infrared astronomy missions, but most interestingly, he's a project scientist for the instruments on the Webb Telescope. So he's got more than 100 publications and received the NASA Exceptional Achievement Medal, as well as the Goddard Exceptional Achievement in Science Award. Anyway, Matt is going to tell us about the Webb Telescope and all the interesting results that we're getting.
All right, thank you everyone for coming out to hear about the Webb Telescope mission. Now, traveling back in time is the stuff of science fiction, but looking back in time is something that we actually do, and that's a big part of what the Webb mission is all about. It works as a result of the finite speed of light. If you look at the person seated next to you right now, you're not seeing them as they really are. You're seeing them as they were a few nanoseconds ago. Why? Because that's how long it takes light to travel 1 meter from that person to your eye. Now, a nanosecond is a really, really small amount of time. So that transmission delay is completely imperceptible to us. But if we look at objects farther away, the effect becomes more pronounced. For example, if we had a magic switch that could turn off the sun, and we flip that switch, it would be 500 seconds before we saw anything happen. Why? Because it takes light 500 seconds to travel from the sun to the earth. So when we look at the sun, we're not seeing it as it is. We're seeing it as it was 500 seconds ago. If we look at the nearest star, we see it as it was 4 years ago. If we look at the center of our galaxy, we see it as it was 25,000 years ago, and so forth. And so as we look at objects farther and farther away with the Webb telescope, we are literally looking back in time to understand how those objects formed and evolved. Now, the Webb mission was conceived in the early 1990s as a mission to connect the dots, if you will, between this famous image, which is an image of the oldest light in the universe, obtained with Goddard's COBE satellite. A Nobel Prize was awarded for this image. And these colored blobs in the image are temperature inhomogeneities that are the seeds from which galaxies will eventually form. Around the same time that COBE flew, the Hubble Space Telescope was launched. And the Hubble Space Telescope then took the deepest image that it was capable of taking, looking as far back in time as the Hubble could look. And it showed us what the universe looked like when it was about 1 billion years old. And so between the epoch that COBE observed where the universe is only a few 100,000 years old, and the epoch that the Hubble Deep Field showed us, when the universe is a billion years old, between this epoch and that epoch, there's a mysterious, poorly studied epoch known as the cosmic dark zone. And this cosmic dark zone is of great scientific interest because that's the period in the evolution of the universe when the first stars and galaxies formed. Why is it so poorly studied? Because we haven't had the right type of observatory in space to study that epoch. And so that was the original impetus for the Webb Telescope project. All right. Now, you've all heard the statement that space is expanding. What do we mean by that? This cartoon is an analogy that tries to explain that. Here you have a loaf of raisin bread dough that's been set out to rise. And imagine that you're seated on one of the raisins. What would you see? You would see all the other raisins moving away from you, and no matter, even though you're not at the center of the expansion, and no matter what raisin you chose to sit on, you will see exactly the same thing. That's a good analogy for what we mean by space is expanding. When we say space is expanding, we don't mean that the galaxies are flying through space, as if they resulting from some sort of explosion, but rather the space between them is actually expanding. Okay, so what does this have to do with the Webb Telescope mission? Well, the primeval galaxies that form in the cosmic dark zone emit their light in the ultraviolet part of the spectrum. And as that light travels to us through the expanding space of the universe, through that expanding raisin bread dough, its wavelength is stretched from the short wavelength ultraviolet to the long wavelength infrared part of the spectrum. So to see that light today, we have to build an infrared telescope. So what do we mean by infrared telescope? Light comes to us in an infinite spectrum of wavelengths, from infinitely short to infinitely long. It's called the electromagnetic spectrum. And our eyes are only sensitive to a very narrow slice of this spectrum. Why? Well, the atmosphere of the Earth blocks most of this light. And there is a transmission window in the Earth's atmosphere that corresponds to this narrow waveband, and our eyes have evolved to be sensitive to that light. That light reaches the surface of the Earth. But there's a lot more light that is available to be seen. Now, everything we know about the universe outside our solar system, and most of what we know about the solar system, comes to us, that information comes to us transmitted in starlight. So to get all the information that nature presents to us about the universe, we as astronomers want all the light. That's primarily why we put telescopes in space, so that we can access this whole spectrum. The Hubble Space Telescope was designed to operate in the ultraviolet part of the spectrum and the visible part of the spectrum. Our eyes can't see ultraviolet light, but our skin could be burned by it if you stay at the beach too long. In contrast to Hubble, the Webb telescope is designed to operate in the infrared part of the spectrum, from the red end of the visible out into the mid-infrared. Our eyes can't see infrared light, but our skin can sense it. If you hold your hands near a warm stove burner or a warm radiator, and you feel the high heat, what's happening there is your skin is sensing the infrared light that's being emitted by the warm object. All right, now the spaces between the stars, the so-called interstellar space, it's not a cold, empty vacuum. It's filled with giant clouds of gas and dust. It's got atoms and ions. It's not an empty place. And here you have an object in space called the Eagle Nebula. This is a giant cloud of molecular gas, and in that cloud some newly formed stars have been born. Those stars are pumping out a lot of ultraviolet radiation, which is breaking up the hydrogen molecules in this cloud, causing it to take on that visible nebulosity. Now, when Hubble, early in the Hubble mission, Hubble took a famous picture of a piece of this nebula called the Pillars of Creation. Now, what we have in this image, these are filaments of a giant molecular cloud, this one, and you see that the filaments of that molecular gas, it's hydrogen gas, are opaque. And that is because there's lots of dust mixed with the gas that's blocking our view in infrared light. Inside these pillars, newly formed stars are occurring, but we can't see them because the dust is blocking the light. Now, when we look at that same object with the Webb telescope, the longer wavelength infrared light can penetrate the dust so that we can get a better view of the star formation action inside these filaments. So you can see in this way that the Webb telescope uses its infrared capability to enable lots of science other than seeing primeval galaxies in the cosmic dark zone. Here's another example of a giant molecular cloud with newly formed stars imaged by the Webb. This brown stuff you see is the molecular gas mixed with dust. Out here there are new stars that are pumping out a lot of UV radiation and pinching on this cloud. That's breaking up molecules in the cloud. You can see hydrogen streaming off the cloud into space. With the infrared light, we can peer into the dust-obscured regions and see star formation action occurring there. We can see formation of these columnar-type geometries like we saw in the Pillars of Creation. There's lots and lots of rich science that the JWST is revealing about star formation for the first time. Now, we know the basics of how stars are formed. We have these giant molecular clouds in space, and those clouds collapse onto themselves due to self-gravity. And when the cloud collapses onto itself, the pressure inside the cloud begins to rise. And when the pressure rises, the temperature rises. It's much like when you fill your bicycle tire at the gas station. The tire gets a little bit warm when it's fully compressed. Same thing happens in the cores of these clouds, only here, the temperature gets really, really, really warm to the point where nuclear fusion can occur, and then the star is ignited. And when that happens, there is typically a disk of material, a circumstellar disk, that forms around the newly formed star. You can think of that as material like left over from the star formation. And there are often bipolar outflow jets emitted by the newly formed star. Now, when planets, these circumstellar disks are of huge interest because they are the birthplaces of planetary systems like our own. And when planets form in these circumstellar disks, they sweep up material from the disk, causing it to take on this sculpted appearance. These are actual radio telescope imagery of sculpted circumstellar disks. This is a simulation of that process occurring. And so you can see that by observing these sculpted disks, we can infer the presence of exoplanets without actually having to see the exoplanets themselves. JWST is using its high-resolution imagery to do a lot of this sort of work. And here's one example of the circumstellar disk around the star, Fomalhaut. This was the prior HST image, and this is the JWST image, and you can see how much more information you get from JWST about the inner structure of this disk where planets are forming. Here's another example from JWST. Here you can see one of these circumstellar disks is seeing edge on. You can see that little line there is this disk seeing edge on, and here is the big bipolar outflow jet shown in the cartoon. This is another object showing the same phenomenon from the cover of Nature magazine. That's the JWST image. And then here is yet another example of star formation with JWST. This is a fairly nearby nebula. And here you can see a newly formed star has eaten out this big cavity in the molecular cloud. And there's a lot of shock-excited molecular emission occurring here. So the JWST is really, really showing a star formation like we've never seen it before. Now, here you have an artist's rendition of the circumstellar disk around our own star, the Sun, alongside a map of where this debris is actually located. These are chunks of ice and rock that are left over from the formation of our solar system. So this material is of tremendous scientific interest. These chunks of ice and rock are called the Kuiper Belt objects, or the trans-Newtonian objects. They exist in the outer solar system, and we put special non-sidereal tracking capability into the Webb telescope to observe these objects and the planets of our outer solar system. Now recently, we used NASA's New Horizons mission to go out and take a picture of the first Kuiper Belt object, take a picture of the Kuiper Belt object for the first time. As you remember, New Horizons was a Pluto flyby. When we finished the Pluto part of the mission, we sent it on to a Kuiper Belt object to take the first image, and this is what we saw. It was surprising. It turned out to be two objects fused together. And this has since been computer modeled as resulting from a low velocity collision, just a few meters per second. It has been shown that objects like this can fuse without either one being destroyed. And this is of great interest to theories of planet formation, whereby planets form from successive agglomeration of small particles into larger ones, eventually producing a planet over 10 to the 8 years or so. So JWST will be doing a lot of work, is doing a lot of work on the Kuiper Belt objects. Now, most of the liquid water in our solar system may not be on the Earth. Moons of Jupiter, Europa and Enceladus, are believed to be ocean worlds. Worlds that contain vast oceans covered by a thick crust of ice. And when tidal forces from Jupiter act on that ice, it cracks and it produces this geyser-like phenomena where this liquid is injected into space through the cracks. And this is an actual image of this process occurring on Enceladus taken by the Cassini spacecraft. So the Webb is studying this ejecta spectroscopically, and on Enceladus, the Webb has discovered that this ejecta is in fact water, and that Enceladus is putting out so much water that there's actually a giant torus water vapor ring surrounding the whole planet. So Webb is finding a lot of interesting results in our own solar system that are very significant for the search for life. The reason this is interesting for the search for life is that here on the Earth, we know from studies of the mid-Atlantic ridge that life can exist, life does exist at the bottom of the Atlantic Ocean, completely disconnected from the sun, thriving on chemical energy from volcanic vents. The same thing could be happening in these oceans that don't receive sunlight due to the thick crust of ice. So the JWST is doing a lot of work here and giving us a new understanding of moons of Jupiter and Saturn. This is JWST's, one of JWST's images of Jupiter. This is Jupiter's great red spot. That's a storm that's been raging on the surface of Jupiter for 400 years or so. The Webb telescope may show us why that spot is shrinking. It is shrinking, and it might tell us why the great red spot is red. We still actually don't know that. The Webb has shown us rings of Jupiter, and it's an amazing photo rings of Neptune seen in detail that we never had before. Our prior understanding of Neptune was from the Voyager spacecraft. These rings contain chunks of ice and rock, and the Webb is designed to be exquisitely sensitive to ice and rock, and so we're seeing great views of ring phenomena in the solar system. Now, when I was a graduate student, there were no planets known outside the solar system. Today, we've identified more than 5,000 exoplanets, and we believe that for all practical purposes, all stars have planets, with the implication that there are tens of billions of habitable worlds in our galaxy. We don't know that they're inhabited, but we know they're there, and we have learned how to study, to search for life on them by studying the chemistry of their atmospheres. And the Webb will do a great deal of work on exoplanets. Let me go back here. All right, so how do we do it? How can we search for life on an exoplanet that is a tiny dot of light that's nearly impossible to see? All right, we do it with a process called spectroscopy. With spectroscopy, we spread light out into its component colors with special optics so that we can see emission of light and absorption of light by individual atoms and molecules in the gas. And we can actually identify which atoms and molecules we're looking at. So here's an example. We have Mars, Earth, and Venus, and here's a spectrum of the atmosphere of Mars, Earth, and Venus. Now, if Earth had no atmosphere, this spectrum would be a flat line. Does everybody know what I mean by a spectrum? This is a plot of brightness on the y-axis with wavelength on the x-axis. And all these bumps and wiggles are due to emission and absorption of light by atoms and molecules in the atmosphere of the Earth. So if the Earth had no atmosphere, this would be a flat line. It's not a flat line, it has all these bumps and wiggles, and that's telling us that there's an atmosphere there and what it's made of. And with this process, we will be looking for chemistry that is indicative of life. And the way we do it is some of those exosolar systems will be seen edge-on by the Webb telescope. And so we have the configuration shown in this cartoon. Imagine we have a star with a solar system that's seen edge-on. There's a planet. This is our telescope producing a spectrum. So in this configuration, we've got the telescope pointed at the star, and there's a planet along our line of sight to that star. We take a spectrum, what do we get? We get a spectrum of the star plus the spectrum of the planet's atmosphere. Now we just wait a little while for the planet to move out of the way, repeat the measurement, subtract the two, and voila, you're left with a spectrum of the planet's atmosphere. Now, making it sound easy, it's actually profoundly difficult. The kind of photometry you have to do to make this work requires parts per million accuracy, but this has been developed into an exact science with the Webb telescope. With the Hubble Space Telescope, and the Webb is doing a great deal of this kind of work. Now, most of the exoplanets that the Webb works on are somewhat larger than the Earth. The Webb can detect water vapor on an exoplanet that's a few times the size of the Earth. If we're searching for life, why do we care about water? It's not because alien life might get thirsty and need something to drink, but rather for the organic chemistry of life to occur on a planetary scale, one has to have a liquid solvent available on a planetary scale, and water is what we're most familiar with. All right, so let's look at some results. These are spectra of exoplanet atmospheres obtained with that transit spectroscopy process that I described. So the first thing you see here is that these are not flat lines. They have all kinds of bumps and wiggles. And so that's telling us that these planets have atmospheres. And we can actually identify the compounds that we're looking at. And we've discovered water and methane and lots of chemistry in these atmospheres that will be the topic of much study over all of the Webb mission. Here is another famous one where we discovered methane and carbon dioxide. And this possibly have detected this chemical dimethyl sulfide. Dimethyl sulfide, if this turns out to be real, is very exciting because on the Earth it's only produced by biology. So this finding here doesn't yet meet the exacting statistical standards that scientists use to claim a discovery. It needs a little bit more observing time, but it's tantalizing and interesting and very exciting. All right, when we first put pencil to paper or marker to whiteboard on what kind of machine we had to build to do that kind of science, we concluded that we needed 7 times the light gathering capacity of the Hubble Space Telescope. And we needed Hubble's ability to see fine detail, angular resolution, as they call it. And we needed to be able to observe in the optical to mid-infrared spectrum to see those first galaxies. And so when we realized these 3 things, we then realized that we had 2 enormous problems that almost stopped the project dead in its tracks. The first was that we had to provide, to get 7 times the light gathering capacity of Hubble, we had to provide a primary mirror that was bigger in diameter than the biggest rocket. That was problem number 1. And problem number 2 is to make an infrared telescope that works out to the mid-infrared spectrum, the telescope has to be very, very cold. Why? Because everything above absolute zero emits light. If we had infrared goggles on, we would see our bodies glowing in the infrared, the walls and floor of the room would be glowing in the infrared. If we didn't make the Webb telescope very, very cold, it would be blinded by its own infrared emission. How cold do we have to make it? Well, really, really cold, almost minus 400 degrees Fahrenheit. And then and now, there's no mechanical refrigerator powerful enough to cool the Webb telescope to such a low temperature. So those were the problems that we had to solve. Obviously, we did solve them, so let's take a look at how we did it. Let's talk about the thermal problem first. The Webb telescope was not placed in orbit about the Earth the way most satellites are. We sent it to a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And this point in space is about 1 million miles in the anti-sun direction from the Earth. All right, how does this help us cool the Webb telescope? Well, as the Earth orbits the sun, okay, this pattern of Lagrange points, of course, orbit with it. And so if an object is placed at the L2 point, one can see that all the sources of heat on that object, the sun, the Earth, and the moon, are always in the same direction. And so then we realized that, well, if we deploy a giant sun shield to block the light from the sun, the Earth, and the moon, so that the Webb will always live in the shadow of the sun shield, we determined that then the Webb would cool passively by radiating its energy away to the cold darkness of space. Okay, so far, so good. However, for this telescope to be useful, it has to be able to point all over the sky, and it has to always be in the shadow of its sun shield. So we sized the sun shield so that the telescope could point 5 degrees toward the sun, we're still in the shadow, 45 degrees away from the sun, we're still in the shadow. So now we have an arc 50 degrees on the sky. Now, you can readily see from this cartoon that if we rotate the Webb about the Earth-Sun line, that's not going to spoil our shadow situation at all. And so this arc turns into an annulus. And that annulus covers 35% of the sky. So at any instant in time, the Webb can point at 35% of the sky and still be in the shadow of its sun shield. Okay, so far so good. Now, as the Earth orbits the sun, we're now rotating about this axis, and so one can see that this annulus will cover the whole sky every 6 months. So every 6 months, the Webb can point at any spot in the sky and still be in the shadow of its sun shield. So that is how we solve the thermal problem by going to the L2 point. We're not exactly at the L2 point, but we're in a small orbit about the L2 point, shown on this little cartoon here. Why do we do that? Well, on the Webb, we're generating electricity with solar arrays. It takes about 2 kilowatts of power to run the Webb. And so it's important that we stay out of the Earth's shadow. And so we went into this small libration point orbit to stay out of the Earth's shadow. There's one other thing, in this little orbit is unstable in the direction of the Earth-Sun line, so it does require station-keeping thrusters to maintain that orbit, and we model that we have about 20 years of propellant on board to do that. Now there's one other thing that makes the L2 point ideal for our mission and many other missions, is that one can see that if you're at the L2 point, the telecommunications range to the Earth will always be constant no matter how long the mission lasts. And that's very important for getting the data back. All right, let's talk a little bit about that sun shield that produces that shadow. The Webb sun shield has an SPF of 1,000,000. If you had this on the beach, you would be very, very well protected. It really is the size of a tennis court, about 70 by 40 feet. It has 5 layers to give it that SPF of 1,000,000. Each layer is made with a heat-resistant plastic-like material called Kapton, and each layer is thinner than a human hair. The sun-facing layer is coated with silicon, so it really looks pink in reality. The remaining layers are coated with aluminum. The sun shield has to have a special curved shape in order to give it that thermal performance and prevent stray light from getting into the telescope. And those of you who sew may quickly realize that in order to make something curved out of flat cloth, you need lots of seams. And so each layer of this sun shield is itself a quilt of 50 pieces. And that involves 7,000 inches of seaming. It's not done with needle and thread, but with thermal spot welds. Developing this sun shield was the hardest part of the Webb mission. And people often ask, what were you worried about, during the launch? It's deploying the sun shield was what I personally was most worried about. It all worked out very, very well. Okay, this is an example of some testing that we did on the sun shield. Here you see the sun shield folded up into a containment pallet, and telescoping booms are pulling it out of that pallet. These mylar tables are there for gravity offloading. They aren't there in space. You can see a person appearing in the center here. That gives you a pretty good sense of scale. If you look closely, you can see the quilting. And there is a cord that runs around the periphery of each layer that's tensioned to give it its precise shape. So after it comes out of the containment pallet, then these spreader bar assemblies around the periphery separate the 5 layers. You get the idea. All right, so why was the sun shield so scary? Deploying it involved 140 release mechanisms, every single one of which was a single point of failure, and yet we got permission to go forward with this design. A lot of moving parts here, 400 meters of cable running over as many individual pulleys. Pretty complicated stuff. It all worked perfectly. Okay, let's talk a little bit about the mirror being bigger in diameter than the biggest rocket. Okay, to solve that problem, we adopted something called a segmented mirror architecture. So rather than build one 6.5 meter diameter mirror, we built 18 hexagonal segments that were mechanized to play together as if they were one big mirror. and that allowed us to fold the telescope up inside the fairing that we use. We launched the Webb on a French rocket, the Ariane 5 cryogenic upper stage, and it's a 5-meter diameter fairing. This rocket is launched from Kourou Launch Center in French Guiana, which is on the east coast of South America. As I mentioned, a lot of moving parts, a lot of single points of failure. The payload is 6.5 metric tons. This is an end view, and so you can see there's not a lot of empty space inside this fairing. All right, the Webb mirror is not made of glass. It's made of a metal called beryllium. Why did we use beryllium? Well, although we adopted the process that I described for cooling the Webb to allow it to get to minus 400 Fahrenheit, as it points to various spots around the sky, there will be small temperature gradients that form in the mirror. And we didn't want those small temperature gradients to spoil the shape of the mirror. So we had to find a material that had a low coefficient of thermal expansion at the operating point of minus 400 Fahrenheit. It turns out that beryllium has that property. The beryllium starts out in a powder form. We compress it under tremendous heat and pressure to form a billet of material. And then after we go through all the trouble to do that, we machine away almost all the beryllium. So this is the back side of the flight mirror, and this is the front, the shiny side. You see lab equipment reflected here. But that's what the back side of a mirror looks like. And as you can see, we're lightweighting the mirror as much as we can. We achieved an aerial density, mass per unit area, that's about 6 times lighter than the Hubble Space Telescope mirrors, and this is the current state of art for lightweight telescope mirrors. Now, we have another problem. How do we polish mirrors? How do we polish telescope mirrors? Well, we rub on them with gritty stuff until they get smooth and shiny enough. That's a room temperature operation. So if we're going to polish the mirror at room temperature and then use it at minus 400 Fahrenheit, that means that we have to put in the wrong shape at room temperature to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so we have to follow an iterative procedure in which we would polish the mirrors part way and then put them in a specially instrumented space simulation chamber at Marshall Space Flight Center near Huntsville, Alabama, where we would cool them down to the operating temperature, observe them with special optics test equipment to see how our model was tracking to reality. Then we would make adjustments to the model and iterate this whole process with the polishing house. This is part of the reason why it took so long to build the Webb telescope, but this was all very successful. This is real data that you see here in the upper right. So this is a flight mirror segment at room temperature. These colors denote topographic relief, so these are peaks and valleys. And we take that mirror and cool it to the operating temperature, it flattens out to have a perfect figure. And we did that for every segment of the Webb telescope. All right, after we got the instruments and the optics all integrated to the telescope, it was too heavy and large to put in any transport aircraft. And so we loaded the Webb, we put the Webb in a special mobile clean room, if you will, a very glorified shipping container. And we used a roll-on, roll-off transport ship. We shipped out of Seal Beach, California, just south of LA, and we took the Webb through the Panama Canal over to French Guiana. It took us a couple of weeks to do that. We had great weather, and this is the first time that NASA has delivered a payload by boat, and it all worked out very well for us. All right. All right, so we're down in Kourou. We're in the vertical assembly building. We're in an elevator that's right alongside the Ariane 5 rocket. There are work platforms set up at various points while people are getting the rocket ready to fly. We're going to the top. We're going to go to where the Webb is being mated to the launch adapter of the rocket. So this is the last view of the Webb telescope on Earth. The spacecraft is fueled here. That's why they're wearing these safety suits. And here we're putting the fairing on. It goes axially for this kind of rocket. And then we roll out on a crawler vehicle out to the launch pad. Of course, this goes very slowly. In real time, you can walk alongside it. And then we launched it.
James Webb begins a voyage back to the birth of the universe.
Okay, we had a great launch. The trajectory correction maneuvers to get out to the L2 point were smaller than planned. That's why we have so much fuel on board to do the mission. Right after launch, the first thing that happened there was you saw the solar rays come out, so we could become power positive. We're on batteries up to that point. The high gain antenna comes out so that we can begin talking to the Webb. We went out to the L2 point on a direct transfer trajectory. We didn't orbit the Earth even once. In this phase of the mission, all went very, very well. The deployments occurred en route to the L2 point. That's how the telescope secondary mirror deploys. There are various radiators deploying. Here you can see the wings of the secondary mirror deployed much like a round drop leaf kitchen table. All of that worked very, very well for us. All right, when we first got on orbit and we point the telescope at a star for the first time, we have 18 separate telescopes because we built the mirror out of 18 segments. And each segment can be adjusted in 7 degrees of freedom, the 6 you're familiar with, plus radius of curvature. And so when we first pointed at a star, we're going to see 18 images of that star. Then we would move each segment to figure out which image went with which segment. And then we would superpose all those images onto one. And then we would use the mechanisms in each segment to make it, adjust it interferometrically to be exactly coplanar with its neighbors. And at the end of that process, voila, you have a nearly perfect image. And so the Webb that worked well. The Webb is exceeding its image quality requirements by about a factor of 2. And this shows the significance of that. It's literally true that the Webb is giving humanity its first high-definition view of the infrared universe. And this is what we mean by that. In circa 2009, we had the WISE mission. The WISE mission was a 40-centimeter telescope, and this is what a typical infrared image with WISE would look like. Then a little bit later, we have the Spitzer mission. That's an 85-centimeter telescope, and you can see that we get a slightly better view because of the larger Spitzer mirror. And then here's the JWST image of this exact, these 4 stars and these 4 stars and these 4 stars. And you can see the stunning clarity of the Webb telescope. And what's going on here is simply given by this equation. The ability to see fine detail is determined by the wavelength over the diameter. So the bigger the diameter is, the more detail we're going to be able to see. And that's the real power of the Webb telescope. Let's look at some other results. We said we wanted to see galaxies in the cosmic dark zone. Here we are able to see galaxies as far back in time as a few 100,000 years old after the Big Bang. We're able to do spectroscopy on those galaxies and actually measure their chemical composition at these very, very high redshift. We're able to measure the shapes or morphologies of galaxies in the early universe, and that's turning out to be a big surprise. We expected the first galaxies to be very irregular in terms of their morphologies, but what we're finding is that we're seeing all kinds of very well-developed morphologies for galaxies. We're seeing spheres, we're seeing disk galaxies, and that is somewhat of a surprise that that aspect of galaxies evolved as quickly as it did. The Webb has teamed up with Chandra to observe what has turned out to be a supermassive black hole that's occurring very early in the universe, which is a big surprise. This might be first observation of black holes that can form by direct collapse of clouds in the early universe that was theoretically predicted, never seen before, but we might have seen it now with the Webb. The Webb is able to see the process of the first galaxies reionizing the universe, making it transparent. Here the Webb is able to look at galaxies backlit by a quasar, and we can see the galaxies ionizing out bubbles in their surrounding medium, and as those bubbles get bigger, they coalesce into the transparent universe that we have today. With the Webb, we're able to see this process actually happening. With the Webb's incredible ability to see fine detail, we get stunning new views of objects that were formerly well studied. This is something called a planetary nebula. It's got nothing to do with planets, but it's what will happen to our star, the sun, when it runs out of fuel. Stars like our sun, when they run out of fuel, they'll throw off their atmosphere to produce a giant nebula like this, called a planetary nebula. This is a famous one called the Ring Nebula, as seen in near mid-infrared with the Webb. And you see all these radial outflows and just tremendous detail that we've never seen before. When stars that are more massive than the sun die, they also throw off their atmospheres, but in a giant explosion called a supernova. This is leaving behind a remnant of the supernova. This is a famous one called Cassiopeia A. This supernova occurred during recorded history. It's only 340 years ago, so people actually saw this. And it's pretty close to the Earth, so we can get a lot of detail about heavy elements being formed in this ejecta. This is where all the heavy elements are formed. If you hear people say, "We are star stuff," that's a literally true statement. The calcium in our bones, the iron in our blood, the gold and silver in our jewelry were all produced in supernova remnants, presumably near the Earth in our case. We've seen an entirely new phenomena that we've never seen before. This is one example. Here you have a late-type star that's undergoing episodic dust formation, producing this incredible bullseye pattern of a nebula surrounding it. And this cartoon is the interpretation of what's going on there. All right, so those are my comments about the Webb for today. What's coming up? Later this year, we have Europa Clipper. It's going to go out to search one of those ocean worlds, Europa, and that we spoke of. It's important for the search for life. Also this year, the Vera Rubin Observatory, a giant ground-based observatory in Chile, will begin operation. And this observatory will usher in a new type of astronomy called time domain astronomy, where the emphasis is on what changes in the night sky over time scales. short and long. Then in 2027, we will put up the Roman Space Telescope, which is being built at Goddard. This will focus on a study of dark energy, high redshift supernova, and it's also developing some exoplanet coronography technology that will feed into the true successor of Hubble, which will be the Habitable Worlds Observer. This will be launched, this will be started in earnest in the next decade, and this is something that NASA's just got permission from the National Science Foundation's Decadal Survey to begin working on as its next major mission. Okay, and that's what I have to say. I'm happy to answer questions for as long as you have.
Well, you've given us a lot to think about. We launched Hubble 34 years ago, almost, on April 1st. I was part of that. And Frank told me at the time, I said, what happens if anything goes wrong? And he said, we're 51 degree launch azimuth, we'll go up and fix it with the shuttle. Which, of course, as you know, we did. It all worked out just fine. And when you go to Lagrangian 2, nobody's going to go up to fix it. Did I hear you say you have 20 years with it?
Right.
So, what happens after that? When you can, at some point, try to launch another facility like this?
Okay. So the question is, what happens
when
when
the Webb runs out of calendar? When it runs out of calendar, it will fall out of that libration point orbit into some general sun-centered orbit in space junk out there. The Webb is not serviceable. It is possible to do a propellant replenishment mission on the Webb. And we did put some stick-on targets onto the adapter ring to enable the vision docking system that we currently use. But there's absolutely no plans to do a mission like that. Whether a mission like that makes sense will depend on what kind of shape the Webb is in at that time. It might not be worth adding propellant to it. You have to always trade that against doing a replacement mission. Now, in contrast to that, the Habitable Worlds Observer, which is just starting now, that will be seriously serviceable.
So, fairly early on, there were some reports that one of the segments was damaged. Can you comment at all about how that has affected the overall performance of these work?
Sure. The Webb, as you saw, is an open telescope. It's not in the tube like the rest. So you have a lot of exposed stuff. And as you know, in space, exposed stuff is going to be hit by micrometeoroids. So that's something that we designed for. And the Webb is hit by those all the time. It doesn't affect performance. Early in flight, we did have a primary mirror segment get hit by a somewhat large one. And that set us back in our chairs a little bit because we were expecting a certain size distribution. And this was 7 sigma out there. We weren't really expecting it. So we got worried a little bit. It didn't damage the mirror in a way that affects performance. I mean, we're absolutely in spec. We're exceeding spec by a lot. We did change the way we operate the Webb in order such that we spend less time with the mirror pointed in the random direction of the orbit. And that will lower the closure velocity of other particles that might be waiting for us out there. But no significant damage done by that. It's not affecting performance. We're going to get hit by more of them. It's not anything to avoid.
What kind of IR detectors are you using on the Webb?
Okay. We're using 2 kinds of detectors. They're all semiconductor detectors. The near-infrared detectors are we involve an alloy of mercury, cadmium, and tellurium. So they're mercad telluride detectors made by Teledyne in California. And then the mid-infrared instrument is also semiconductor. Those are silicon detectors that are doped with antimony. And so they are made by Raytheon Vision Systems, and that technology is now over the aft horizon. So this is the last mission that will use semiconductors in the infrared. Doped with arsenic, I'm sorry.
Any other questions?
Did you have trouble digging up enough beryllium?
No, actually, beryllium availability wasn't a problem back in those days. We're using a special optics grade beryllium called O30 powder invented by the Air Force. And what that simply means is the grains of the beryllium will be molten, dropped from the shot tower to make them form spheres. And that causes a more stable material when you compress it.
So if you have time, you didn't really get into the instrument so much, it wasn't part of your talk, but I know that the near spec, the spectrometer detector was formed with a lot of little mirror sets, right? That formed this.
Microshutters?
Microshutters, thank you. Just wondering how the performance of that is going. There were some problems, I know, with some of them prior to launch, so they didn't all work right, even at launch. Just wondering what percentage is problematic right now,
Yeah.
and
So,
just how it's doing overall.
so one of the problems we had to solve, we want to observe these primeval galaxies in the cosmic belt. They're super faint. So to observe one, you have to stare at it for a long time. And we quickly realized that if we just did that, we would never be able to observe enough of them in the mission. So we had to develop something called a multi-object spectrometer. This is a spectrometer that can observe lots of objects simultaneously, keep their spectrum all separate. And so this near-spec instrument, the main near-infrared spectrometer out of that, is actually the first multi-object spectrometer to fly in space. And to give it that multi-object capability, we had to invent an aperture control system that would allow it to target up to 100 different galaxies anywhere inside a 9-minute box on the sky. And we competed lots of different ideas on how to do that together, and eventually selected something called a microshutter array, which is an array of microscopic shutters that are computer controlled so that we could open any pattern of shutters we want to match a particular star field, letting light from the desired targets into the spectrometer and blocking everything else. And so that was a hard job. We really had to develop that from scratch. And they were working okay. They were working fine. It was a long slog to get that to the point where we were going to launch it, but it's working fine. And we've gone on to develop several generations beyond what's flying in the Webb now for habitable worlds observed. Yeah.
You mentioned fuel as maybe the limiting factor. What about batteries, gyroscopes? How are they?
The rest of that should last forever. The gyroscopes, they're not like Hubble. They're built with parts. And yeah, the propellant is the only thing. The battery is just floating in the system. It's not used operation. So.
I was familiar with the move, of course, through the Panama Canal Roll. Always worried about all that. In '97, we took a trimmed spacecraft to Kagoshima, Japan. We cranked up 2 Air Force C-5s. I was in the navigator seat for one of them. It was a 19-hour double mid-air refueling. And then we had to put that spacecraft in this little freighter going from Kagoshima over to Tanegashima. And I supposedly, with Tom Lavinia, had to make the decision, do we sail or not? We're going to time out in 72 hours. The harbor was nice and smooth, no problem, but outside it was wild. And I figured it's one of those deals where you get the picture on Time magazine. If the billion-dollar spacecraft sinks, you get it over there, nothing ever happens again. We got it over there. We successfully got it launched. We launched in the Japanese H-2 rocket, and they were going to launch something before us, and they had a problem with their spacecraft. And they wanted us to put our spacecraft on their booster. We decided, no, we've signed up and paid for this booster. Theirs failed later on, ours went dormant.
Yeah.
I was not going to make that decision. That's a headquarters decision.
My side is 20.
Yeah.
What's the expected lifetime of Webb?
Well, as I said, we had 20 years for propellant, so we hope to last.
Good.
You said the propellant was, you didn't need as much. What was the original spec?
The original was 10. But Arian, they gave us such a precise launch that now we're fat.
Any other questions?
That's a great question.
Repeat the question.
Is what, when the Webb mission is over, what fraction of the sky will we have observed? What fraction before pi will have been observed? I don't know the answer to that. It is known, though, because we know what Hubble has done for, since its launch. The Webb will be about the same.
Yeah. You mentioned it will have a capability of being refueled. So that's still a potential option.
Well, the capability, as I said, we use the fill and drain valves that have already been demonstrated as being robotically, that you're able to deal with them robotically by cutting the safety wires and mating them. They've already demonstrated that. We put a vision docking system targets on the adapter ring. That's all we've done. There was no plan at NASA headquarters to service the Webb. There's no plan anywhere to service the Webb. But those two elements of capability are in place.
How long will it take to develop a plan?
Oh, it would take just a few years for the plan to be. But it'll boil down to what kind of shape the Webb is in, if it needs it.
Where is the Webb telescope controlled from?
Great question. It's controlled from the Space Telescope Science Institute in Baltimore.
Oh, well.
We're using the Deep Space Network. Data go, we're using 3 DSN stations, and the data then from the DSN is transmitted to the Institute in Baltimore via the internet. Ground processing occurs there, and then it's transmitted from the Institute to the astronomers again via the internet.
I assume it's all KA, KU for cheapers?
It's KA bands for science data, and I think we're using S band.
Yes.
Yeah.
I've got probably a dumb question, but I know the star system, the spikes are because of the shape of the individual mirrors, but that doesn't explain to me why they happen.
These are diffraction spikes, and they occur from the edges of the mirror segments. And this particular pattern of diffraction spikes is different than Hubble and a lot of other telescopes, and that's because of the tripod that holds the secondary mirror, puts its little imprint on that. And so you get this diffraction pattern that's unique to JWST.
Why just that one? On that, why do you just see one?
And that's a real bright star, see?
Because it is the brightest.
Yeah, just right.
They show up with point sources, right? If you have an extended source like a galaxy, you don't get that same.
Right.
All right, let's thank our speaker again.